The sky still glows with the universe's baby light. That glow is the cosmic microwave background, the oldest light visible. It preserves a fossil record from 300,000 years after the Big Bang. So the CMB is effectively a baby photograph of the cosmos. So remember, ancient light maps the early universe. A faint, uniform glow fills the sky in every direction. That glow is the cosmic microwave background, leftover radiation from the hot early universe. It matters because the glow preserves conditions from the universe's first moments. Early, the universe was a hot plasma of photons, electrons, and protons. Photons scattered constantly, and light could not travel freely yet. When atoms formed, photons decoupled and streamed across space. Today, the radiation has cooled to about 2.725 Kelvin, so the CMB is ancient light we can still measure. Picture a modeled map with tiny hot and cold spots across the sphere. Those differences are anisotropies, minute temperature variations in the CMB. They matter because they seeded every galaxy and cluster we see. Gravity pulled tiny overdensities inward, while radiation pressure pushed outward. That tug-of-war created sound waves in the primordial plasma. When photons decoupled, the pattern froze, leaving preferred angular scales. For example, the first acoustic peak corresponds to about 1 degree on the sky. In short, anisotropies are the blueprint for cosmic structure. Now picture the CMB spectrum as a flawless thermal curve. It follows a nearly perfect blackbody distribution at microwave frequencies. This matters because a blackbody confirms the universe was once hot and dense. Any energy injection after recombination would slightly distort that curve. Processes like early stars, decaying particles, or shocks would leave tiny fingerprints. Current measurements limit distortions to less than 1 part in 10,000. For example, COBE measured deviations smaller than 1 part in 10,000. So the pristine blackbody shows the thermal origin of cosmic light. Telescopes sweep the microwave sky, collecting faint photons across frequencies. CMB experiments map temperature and polarization to microkelvin accuracy. Precision matters because foregrounds can mimic primordial signals. Instruments compare maps at multiple frequencies to separate galactic emission. They use detectors cooled to near absolute zero for sensitivity. Missions like COBE, WMAP, and Planck improved resolution and frequency coverage. For example, Planck mapped temperature fluctuations at microkelvin precision across billions of pixels. So instrumentation turned faint microwave noise into a precise cosmic blueprint. A faint twist in the light reveals directional patterns across the sky. This is CMB polarization, caused by scattering at last interaction. Polarization matters because it can reveal primordial gravitational waves. Density variations generate E-modes, which are already well measured. Primordial gravitational waves would produce B-modes, a smoking gun. Measuring B-modes requires exquisite control of foregrounds and systematics. For instance, Bice-Petwo initially claimed detection, but Dust explained much of the signal. So polarization is promising, but also technically delicate. Numbers on CMB maps translate into the universe's vital statistics. Cosmologists extract parameters like age, composition, and expansion rate. These parameters matter because they anchor every cosmological model. The acoustic peak's positions and heights constrain matter and energy fractions. Statistical fits to the power spectrum yield precise numbers for each parameter. For example, the CMB indicates an age near 13.8 billion years. It infers roughly 70% of the universe is dark energy. Dark matter makes about 26%, baryons about 4%. Bottom line, the CMB calibrates the cosmos with striking precision. Future maps will be sharper and they will probe subtler signals. Next-generation surveys aim to measure faint polarization and spectral distortions. If detected, those signals could test inflation and reveal new physics. They rely on huge detector arrays, cryogenic receivers, and precise calibration. Ground and space missions will combine sensitivity with broad frequency coverage. Projects like CMB-S4 and LiteBIRD plan orders of magnitude more sensitivity. For instance, some experiments target tensor-to-scalar ratios near 0.001. So future CMB work could confirm inflation or surprise us entirely. We started with the baby light and it still guides everything. If you enjoyed this, subscribe for more clear cosmic stories.